Hi engineering students, this is the second video in the second week, week 2B. Hope everyone's getting off to a good start. We're not going to have so much housekeeping this time in this video, so I hope this will go a little shorter. I'm going to aim for less than the 55 minutes that we did last time. Don't forget, I am trying to move quickly though to get through everything. So that's the whole point of the recorded aspect, is you go back, you re-watch it, you ask me questions on the discussion board. I also had one good question from Teleos this week. Should you watch the video first or should you do the reading first? I would say do the reading first. I think you could do it the other way around, but I'm really mostly going to be explaining what's in the book and expanding on it. So I think it'll make more sense if you read, then watch, okay? Now we are going to start right away with right angle trigonometry. We are on kind of where that heading is down the bottom of page 26, tackling the three basic identities of trigonometry. There it is down the bottom. And they summarize this very, very quickly. Let me open up the whiteboard and we will start to show you how this looks. Now the Pythagorean theorem, this is where we left it last week. And yes, I'm going to drop my camera. Uh-oh, hold on. I'm just going to point the camera at the ceiling. The Pythagorean theorem only deals with side lengths. Okay, here we go. That's distracting. Speaking of distracting, how about that? Pythagorean theorem deals only with side lengths, and we want to give some important rules for triangles that also bring in the angles as well. I don't have to tell you that any triangle that you can see has 1, 2, 3 angles and 1, 2, 3 sides, and all those are of interest. Now we are going to be dealing exclusively, of course, with right angle triangles. Okay, everything I say today will only apply to right angle triangles. That's where there's a little right angle in the corner, and it doesn't matter, you know, what orientation that is, as long as there is one right angle. Now, the whole point of what we're going to say today is that a triangle is such a simple shape that if you can define the right angle, that's as in the 90-degree one, and then if you can define another angle and another side length, you have just guaranteed the outcome of the whole triangle. Let me say that again. Once you have a 90-degree established, as I do in both these two pictures, if you can tell me what one of those angles is, and if you can tell me what one of those sides is, like let's say we say this is 30 degrees over here. I'll go for a slightly thinner pen, hold on. And then if you can say this side length is say 25, whatever it may be, centimeters. If you can define two things, one angle, one side, then all those other sides, okay, this side here, and also this angle here, those are all suddenly now absolutely determined. They're locked down. They have a definite outcome and there is no doubt about what they are, because that's how triangles work. Once you define a couple of things, the rest of it is also defined. It also, in another way of saying this, let me erase this thing right here. Once you have two right angled triangles that have a similar ratio of sides, it also guarantees that the outcome of the angles will be the same. And here's what I mean by that. If you have a right angled triangle, actually I'm just going to clear the whole screen. Let's go from the start. If I have a right angled triangle and let's say it has legs of length, let's say 4 and 6. Okay, I'm trying to do this really carefully. There's a right angled triangle. This is 4 units, this is 6 units. All right. Now, if I have another triangle nearby that has legs that are exactly double that, let's say Here's one that has 1, 2, 3, 4, 5, 6, 7, 8. And then double 6 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we make a triangle out of that. There's the right angle. 8, 12. Now, because these two triangles have similar ratios of sides, that means the angles in those two triangles are also going to be the same. Like this angle here, whatever it is exactly the same as this angle here. This angle here must be the same as this angle here. These are what we call similar triangles, okay? And it's all defined because we have a couple of pieces of information, and that's all you need, and that locks down the outcome of the whole triangle. Okay, these are all kind of the basic rules before we get into it. Now let's start by defining a few things. As we look at any given right angle triangle, we always have something that we call the hypotenuse. Okay, hypotenuse is that long side. Okay, it's this one right here. That is always the hypotenuse. It's the one that is opposite to the right angle. Over here, it's this one. And that doesn't matter if the triangle is like rotated, is facing a different way, it doesn't matter. It's that long side that is opposite the right angle that is called the hypotenuse. We call the other two sides, these are called the legs, okay? Leg 1, leg 2. These are the legs of a right angle triangle. 2 legs, 1 hypotenuse. We also, I've already been using the word, but when it comes to the word opposite, that means something very significant in right angle triangles. When you pick a particular angle, okay, let's say we pick this angle, let's call this angle A. This side over here, this is the opposite side to angle A. And it's not too hard to see why that is. It's, you know, if you want to say it's the side that's furthest away from the angle. Let me do another one over here. If I said this was a particular side called side F, just to pick a letter of the alphabet, then this angle over here is opposite to that. Okay, so you have opposite sides and angles when they're like that. All right, there's some basic definitions. Let's keep on moving. It's going to get clearer as we go along, and obviously for some of you, this is old hat. You've done this many times. And for you incoming 9th and 10th graders, you will be very familiar with this before long, and also in your regular math classes. Let me start with a 45, 45, 90 triangle. What I mean by that is the angles are 45, 45, and 90 degrees. Okay? I'm going to do the same little angle symbol in both corners, because they're both the same. We know that the interior angles of a triangle add up to 180, and that's what I have right here. This is the 90, those are the two 45s. That adds up the sum of all angles. We did this last time. The sigma notation is 180 degrees. Okay, and that's why we call it a 45, 45, 90 triangle. I'm going to start by picking one of the two angles to be what we call the reference angle. Okay, here we go. I'm going to pick this one right here. I'll mark it in blue. That is our reference angle. In other words, that's the angle that's going to define what I do next. That's the angle which things will refer back to. Once I pick the reference angle, I'm going to label the rest of the triangle according to that reference angle. Now, the first label you do is the hypotenuse. That never changes. That's always just that long side opposite from the 90 degrees. But because I chose that blue one there as the reference angle, I now label this leg as the opposite leg, or the opposite side, and I label the other leg as the adjacent side. Okay, Now, when I say opposite and adjacent, I already talked about opposite earlier. Opposite means it's the one that is opposite to that angle. It's like the furthest away side, if you like. But adjacent, that's a new word. Adjacent just means touching or next to. This is the one that is touching or next to that blue reference angle right there. Okay. Now, it's important to realize that you can only label which one is the opposite and which one is the adjacent sides after you choose the reference angle. Okay. Step one was to choose the reference, and then you can say which one is which. Okay. Now, we have labeled those three sides. And now there are three functions that we need to learn. Now, a function, I know I'm giving maybe some new words to 9th and 10th graders. A function is just like a mathematical process or machine, or like a mathematical it's almost like a computer program or something, where you put in a value and then you get out a particular value. And the three functions that we are going to use in this course are called sine, cosine, and tangent. Now, if you have a scientific calculator, either on your computer or physically next to you, like I do, then you have seen these buttons on your calculator. They are abbreviated to SIN, COS, and TAN. And you may have wondered what those were. I remember as a student in like middle school sort of era, wondering what those were and how you say them. First of all, you don't say sin, you always say sine, but it is acceptable to say cos and tan, okay? But sine, cos, and tan, they stand for sine, cosine, and tangent, okay? If you don't have a calculator, by the way, you should have one, either on your screen or next to you. I don't recommend like the Google, calculator in the browser. It's much better to have a separate app that's running that won't be interfered with at all. Okay, so these three functions, these all have to do with triangles. And what that number represents, the number represents the ratio of the side lengths, okay? All three of these represent a particular ratio between the different side lengths. Now, you know what a ratio is. A ratio is like saying, like 2 to 1 or 3 to 5 or things like that. If you are into, TVs and media, your TV might have a 16 to 9 ratio. And, it's talking like the ratio of the length to the width, or the ratio of blue marbles to red marbles, or whatever it is. But those are what ratios are, and I think you know about that. Come on back. There we go. So sine, cosine, tangent, they all refer to ratios between different side lengths. And here is what those ratios are. The sine of a particular angle, and I'm going to use this symbol here. This symbol here is called theta. Theta. And it just means an unknown angle, okay? Just like we use things like X and Y and Z for unknown numbers, theta represents an unknown angle. And by the way, in this case, it is our reference angle, okay? This theta is referring to that wonderful reference angle, which I already labeled over here on the triangle. And I will talk through what we mean. I know we're going fast. Sine of the angle is the ratio between the opposite side and the hypotenuse, like the length of the opposite side and the length of the hypotenuse. Sine of the angle, sine of theta, is the ratio between the opposite side and the hypotenuse. I'll say them all up front. Cosine of theta is the ratio between the adjacent side, ADJ, that says, and the hypotenuse. And tangent of theta, is the ratio between the opposite side and the adjacent side. Now, this is what is in your textbook on page 27, so it's right there for you. I do recommend copying it out because this is vital stuff. Now, that seems like a big wall of information to try to remember. So the acronym that people have created to remember this is taken from the first letters of each of those little statements. You've got S, O, H, C, A, H, and T, O, A. And if you put those all in order, you get SOHCAHTOA, which, as the book says, kind of sounds like a Native American name, SOHCAHTOA. Sine opposite hypotenuse, cosine adjacent hypotenuse, tan opposite adjacent. Now, I'll show you how to actually use this right now, but that is the definition of what that means. So we can only do this with a calculator, by the way. Well, I mean, well, there are some other ways to do it, but let's just focus on the calculator idea for right now. You get your calculator and get it right now, you know, switch apps or whatever you're doing, and actually type in sine of 45 degrees. And I'm doing that right now. Sine 45, and I press equals. And what you should see come up on the screen is 0.7071 and so on. Okay, that's 4 significant figures, by the way, which is a kind of a standard number. Okay, sine of 45 is 0.7071. Now, if you didn't see 0.7071, it means you're doing something wrong. It means you possibly are in the wrong calculator mode. You might be in radians by mistake. Okay, and generally in this course, we probably don't want to be in radians mode. We want to be in degrees mode. If you're a calculus student, you got to watch out, because in calculus, you're almost always working in radians mode. Okay, but go back to degrees for this class in general. If you don't know how to do that, you might need to ask me or look it up, because every calculator is a little different. Also, if you didn't see that same exact number come up in front of you, it might be that your calculator accepts the input in a different way. You might have to type 45 first and then press the sine button. Okay, so if you didn't get it, try that. Just pause the video, try to find out how to switch modes, or try to type it in backwards. I can't stand the ones where you go to type it in backwards. Mine, you type literally sine, then 45, then equals. Now try again with cosine 45. Again, pause the video, try that out, see what you get. What you should come out with is, coincidentally, the same exact number. I am not going to go into the reasons why that is in these lessons. I'm just giving you like the, you know, the quick and dirty method on this one. And then you do tan of 45. Again, pause the video, try that out, see if you get the right number. You should get the number 1. Tan of 45 is exactly 1. Exactly 1. Okay. So what this is saying is that 0.707, let's start with that one. 0.7071, that is the ratio between, I'm going to box it right here again for you, between the opposite side and the hypotenuse of this particular triangle. 0.7071. If you want to think of that instead, maybe it's more helpful, you might want to think of that as 70.71%. Maybe that's easier to think of it like that, okay? It's about 71%. So what we're saying is the opposite side, maybe I'll even write it here. It's just saying the opposite side is 71% of the hypotenuse. And we're talking length here, okay? When sine 45 tells you 0.7071. That is telling you that the ratio of the two sides is like 70.71%. That the opposite side length is 71% of the length of the hypotenuse. And if you actually got a ruler out right now and held it up to the screen, you would find just that, okay? To go into the next one, the cosine of 45 degrees is also 0.7071. And by the way, they won't always be the same, okay? Usually they are different numbers. This is a unique case, but that's fine. So that is referring back to here and telling you that the ratio between the adjacent side and the hypotenuse is also about 71%, okay? This length of this adjacent side is about 71% of that length of the hypotenuse, all right? That is what that number tells you. And that may not seem like a big deal, by the way, but it's a huge deal. Okay, bridges have been built and rockets have been sent to the moon based on these principles of triangle ratios. I am making no exaggeration there. The last one right here, if tan of 45 equals 1, that's a bit of a tricky color to see. Let me try that again. Let me give it a light blue. If tan of 45 equals 1, that's referring over to here because tan is defined as opposite over adjacent. That's saying the ratio between the opposite side and the adjacent side is exactly 1. In other words, 100%. In other words, same as each other. And you can see that on the diagram, the opposite side has a length of exactly 4 units, and the adjacent side has a length of exactly 4 units. It is a 1-to-1 relationship. That's why it says 1. Okay, that's what that means. The opposite side is 100%, no more, no less, of the adjacent side. Okay. I am going to jump to a new screen and just give you a little practice problem on this, okay? A little practice problem. And yeah, I'll show you how a typical problem looks. Here we go. A typical problem will go like this. You'll have a triangle, just like that, with a right angle. Remember, it has to be a right angle for this whole idea to work. And let's see. You'll often be given one side length, and forgive me, this may not be to scale. Yeah, this is not going to be to scale. I'm just going to make up some numbers here, so don't read the graph too carefully. Let's say we have 100 inches for our hypotenuse. And then remember that what we do is we select the reference angle. We have to pick one angle to be the reference angle. Is it going to be this one or this one? I'm just going to pick this one. I would say this looks like about 30 degrees. Now, because I chose that to be the reference angle, that means this side over here now becomes the opposite side. And this side over here now becomes the adjacent side. It would have been the other way around if I had chosen this angle up here, but I didn't. And now what you do is this, you say, all right, sine of 30 degrees equals, you might also say cosine of 30 degrees equals tan of 30. You can calculate any of these. Remembering that sine tells you the ratio of which two side lengths. Sine refers to the opposite over hypotenuse. Let's start with that one. You go to your calculator and you type in, all right, sine of 30 degrees, click, 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 tap, 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 enter. Ooh, look at that. It equals exactly 0.5. Exactly 0.5. Sorry, I don't know why I'm just going over and over there, trying to make my, you know what? Let me do that again. 0.5. So that tells me now that the ratio between the opposite side and the hypotenuse is 0.5, or if you prefer, like 50%. It's 50% of the length. Now, what is 100 times 50%? Well, it is 50. So this side length I can now confidently label as being 50 inches long. All right. I just used right angle trigonometry to find the length of a missing side length based on one side and one angle. You can play that video, you can rewind and play that bit again if you want to see that again. For cosine, cosine is adjacent over hypotenuse. And so you tap out, what is cosine of 30 degrees? Well, it is 0.866 and more numbers beyond that. And by the way, if you're new to this and you're bothered by all the messy decimals, there is actually an exact representation of that number, but I'm not going to tell you because we don't really need it for this course. But in your pure math class, you definitely will learn that. So again, you can kind of think of this as saying, you know, this is like 87%. So that means that the adjacent side length is about 87% of the hypotenuse. Now, obviously, you can see how I chose really easy numbers. 87% of 100 is 87. So this side length here is about 87 inches. And if there are any shrewd ones among you, you might realize that I've actually broken the rules of significant figures when I did this. 100 inches, by what we said in the last video, is only one significant figure. Okay, the hypotenuse I gave in one significant figure. So when I wrote 50 inches, that's acceptable because I preserved only one significant figure, okay, the 5. But when I wrote 87, I was actually giving it a little more precision than I should have. Now, I spoke to Mr. Hurt about this just this morning, actually, and he told me that it is actually acceptable to say that 100 inches is 3 significant figures, but it's not clear if it is 3 or 2 or 1. It could be 1 or 2 or 3. Maybe you do mean that it is actually exactly 100. Ask me more about that if you're interested, but I'm just going to keep my 87 inches for now, and we'll leave it at that. But in case any of you are wondering, and the one other piece of information I have not filled out is this other side length over here, and we know what that is, not really through like this kind of trigonometry, but just through the basic fact that the sum of all angles is 180. So this must be 60 degrees. Now, what I just did then, this is called solving the triangle. To solve the triangle means to find all of the angles and all of the side lengths when you only had a few of those things to begin with. Okay, so that was solving the triangle. And it's easiest when you have a hypotenuse and one of those angles. It can get a bit trickier, and there are some cases where you actually can't solve it. But what I did just now, this is the kind of work we'll be doing from here on. So this example on the screen is very important. By the way, I left off the tan, opposite over adjacent. Tan of 30 degrees is, tap, 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 is 0.577 and then some. So that's about, again, like about 58%. And what that is telling me is that the opposite, let me use some color coding, the opposite side, which is this one right here, compared to the adjacent side, it's only about 58% of its length. Now we could show that like this: 50 over 87, that's the ratio I'm talking about. And if we actually calculate that out, 50 over 87, we get to 2 significant figures, we get 0.57. Okay. In other words, that's the same number. It's supposed to be the same number. It's trying to be the same number. If I'd preserved more accuracy along the way, it would have been more precision along the way. But there it is. That's the ratio between those two sides. Okay. 9th and 10th graders, This will not feature heavily in this assignment, in fact, hardly at all, but it is going to come up later. So I wanted to give you the intro to it. You're kind of off the hook for this week, actually. Not so for 11th and 12th graders. You need to be pros at this, and I suspect that you are. If you are a pro at this, then I apologize for taking up half an hour of your time. Let me keep going with just another few things today. Firstly, 12th graders, there was a section on page 27 to page 30, and enough for me to say that calculus features heavily in engineering. We are not going to use calculus methods, but I will record just a couple of special videos later in the year so that you calc students can, cut your teeth on some of the things that we do, because you're learning it so you can use it. So probably second semester, might try some of that. Maybe near the end of this semester, we will see how we do. But now I want to finish with talking about units, because the reading for this week was actually, the second half of this week was actually on units. And so that's really what I want to hit. And I'll just do this one pretty quickly because the book explains it pretty well, but there is a lot there. First up, there are 3 unit systems. There is SI, metric. There's another one which goes by many names. In this book, they tend to call it US customary, but it also goes by the name of imperial, as in like Imperial England. Goes by English units, as in England, not the language. And it also sometimes goes by FPS, or foot-pound second. Now, SI is a French word. It's there on page 32. It's the Système International Unitaire, and that means the International System of Units. It's actually technically incorrect to say the SI system, because the S stands for system. That's like saying ATM machine or PIN number. But the SI unit system, it's hard to not say it that way, is made up of 7 base units. And it's really fascinating, but the SI unit system is 7 units which define everything that we think is measurable in the universe, with just 7 different things. We measure length. I'm going to put it, the actual unit. We measure length in meters, little lowercase m. We measure mass in kilograms, lowercase kg. We measure time in seconds, lowercase s. We measure luminous intensity in candela, lowercase cd. We measure the number of things with the mole, lowercase mol. And we measure electric current in amps or amperes, which is a capital A. And we measure temperature in Kelvin, capital K. Okay, that was meters, kilograms, seconds, candela, moles, amperes or amps, and Kelvin. Those are the 7 things which can be measured in the universe. All other things which can be measured are made up of combinations of those. That's the SI unit system. It is a fascinating thing, and you should learn about it if you can. But what we really will use more is what we call the metric system. Metric is based on the SI units. Okay. Metric is like a bigger idea than SI. SI is like the pure concept of like, what's the minimum number of things needed to define the universe? And metric then branches off and has like all of the prefixes and all of the derived units and all sorts of other things. So that's more the camp that we live in, or the US customary system, as we will call it. Let me spend most of my time here talking about the metric system, because SI is more of like generally more used by like scientists, like physicists. Metric is used more by chemists and all sorts of sane, rational people around the world, engineers, scientists. the metric system firstly has these prefixes. The table is on page 33, and I do want you to be familiar with these particular 7 prefixes. You've got giga, capital G, mega, capital M, kilo, lowercase k, and then to make things smaller, you've got centi, lowercase c, milli, lowercase m. You've got micro, and I'm sorry about this, but it is a Greek letter. It's the Greek letter mu. It looks kind of like the letter U with a tail in the front. Practice writing that a few times. It's like a lowercase u with a leading tail in the front. And then we have nano, which is a lowercase n. So giga, mega, kilo, centi, milli, micro, nano. And these things, I don't need to rewrite that whole table, but giga multiplies something by 1 billion. Mega is by 1 million. Kilo is 1,000. Centi is 100th. Milli is 1,000th. Micro is 1 millionth. And nano is 1 billionth. And we also have the exponentials that they show you there as well. Now, centi is a little bit questionable. It doesn't really like match the others. The others all, you know, like milli matches to kilo, micro matches to mega, nano matches to giga in terms of like a billionth or 1 billion times. Centi doesn't have a little matchup guy. There is one and it escapes me right now. And it's just not really used. But we do have like the centimeter. That's why I mentioned centi, and they measure it as well. Now, before I go any further, I'm well, I promise you. You've got to really get it right when it comes to upper and lowercase. Do not take liberty with this. This goes for units. Units, by the way, are things like, you know, meters, seconds, Kelvin, and so on. This goes for the prefixes. The prefixes are the things that I just went through, things like giga, mega, and kilo, and so on. And it also goes for what we call the symbols. The symbols are the things that, like the type of thing that we measure, not the units we use to measure with, but the type of thing. So we have like, you know, power. Power is a thing that can be measured, and that's capital P. Area is a thing that can be measured. We use capital A usually, or sometimes capital S. Velocity, lowercase v. Okay, these are all things that can be measured. The units are the units that we use to measure them with, and then the prefixes are what we tack on to make those units bigger or smaller. So you might say, how much power is being generated right now by that particular lightning bolt? And my goodness, I can't remember what the number is. It's like, what is it, 1.28 gigawatts? I don't remember. But you could say power equals 1.28 gigawatts. So let me show you really clearly here. We've got symbols here. P is the symbol. I'm sorry, I'm actually going to underline. P is the symbol. It's power, the thing that can be measured. The units to measure that are the watts, okay, which is capital W. And then the prefix used to modify that unit is the G, the giga. And it is pronounced giga, not giga, despite Back to the Future. Okay, so all three of those things appear. And you can't mess with whether they are upper or lowercase. Like you can even see here in the table, if you change milli and mega, if you get that backwards with upper or lowercase, you change it by a million millions, okay? So you have to get that correct. You just have to. Don't mess with it. So here's a few right now for you to just kind of practice, I guess. here are some units. Capital GW would be gigawatts. And when you write it as a word, you are supposed to use all lowercase. I actually got this wrong for a lot of my life. You write it as a word all lowercase every time, even when it's named after a person. Watts are named after Isaac Watt, a British scientist. Capital M, capital J. That is a megajoule. Again, named after a scientist, Mr. Joule, but you got to keep it lowercase. CG is going to be a centigram. In other words, a hundredth of 1 gram, which is not much. MM is a millimeter. NM is a nanometer. Nanometers are what we measure like the wavelength of particular frequencies of light, for example. Lowercase k, uppercase n is a kilonewton. In other words, 1,000 newtons of force. And then Gee, actually, no one says µs, come to think of it. We always just say microsecond. Yeah, that's funny. The others I can say kn, but when you say it out loud, you're just going to say microsecond. You wouldn't actually say kn, I guess you'd say kilonewton, just for the purpose of this little exercise I was doing it. Okay, microsecond, which is a millionth of a second, which is a very short amount of time indeed. Okay, I'm going to try to start to land this plane. I think I've given you most of what you need right now. A few other points is we don't typically use prefixes for US customary units. He makes one obvious exception, obvious to me, not to you, is the kip. A kip is the same thing as a kilo pound. Whoa, what is going on there? A kilo pound, okay? 1,000 pounds. You will see that. Some other stuff is that when you are multiplying and dividing things of different units, the units actually travel through the equation. I did this in the previous video as well. Let me show you what I mean by that. Here's a formula. W equals Fx. Now in this formula, tell me, are these all prefixes? Are these units? Or are these symbols? Prefixes, units, or symbols? These are all symbols. Okay, these are things that can be measured. W equals Fx. This is the formula for work when you are pushing an object with a particular force for a particular distance. This is work equals force times distance. W equals Fx. Now, because force is measured in newtons and distance is measured in meters, the units are going to be, here you go, newtons times meters. This is a common notation, by the way. The square brackets make it clear that I'm referring to units. That's a common notation. So because I multiplied the force by the distance, maybe it was 1,000 newtons times 2 meters, then the units just get multiplied as well. So if I had work was equal to 1,000 newtons times 2 meters, the answer would be 2,000 Newton meters. Okay, and what I just did there, by the way, you can write n dot m. You can also write n hyphen m, but I would say the best thing to write is just nm. Okay, in the strict SI system, you can only write it without the dot and without the hyphen. You just got to do it exactly as is, just like that. One more for you here. Another example. Pressure is force divided by area. Again, these are all symbols of things that may be measured. Force is measured in newtons. area is measured in square meters. Therefore, the ultimate units for pressure are newtons per square meter. So you might have 5,000 newtons that have been applied to 10 square meters. Your answer is going to be 500 newtons per square meter. Some of you know there's another step after that that we do with the Newton per meter squared, but I'm going to leave that for today. Good. I think that's it. That seems like a lot, and I know it seems like a lot. This week, it's all these introductory bits and pieces, and we're all coming from different levels. I'm trying to bring us all onto the same virtual green grid page. It is going to get better next week. We're going to start looking at vectors. We're going to use some trigonometry to do that. It's going to be a little more like concentrated topic by topic, and you guys are going to do just fine. I'm looking forward to continuing on. I'm looking forward to seeing your comments and your questions. Please do look at the questions other people write as well, because man, there are so many good questions coming and you want to get those things clarified. We're going to make you guys engineers this year, and in a few weeks I'll also unveil what the awesome project is that we're going to do. It's going to be collaborative, it's going to be helping people, it's going to be local, organic, all those things, and we'll look at it then. Thank you so much, and I am going to work out how to stop this recording. See you guys later.